Okay, welcome everyone to this semester's Data Science for Energy System Modeling. My name is Fabian. I will be guiding you throughout the semester. We have a bit of a novelty this semester, and I have to start with that straight away. So this semester, this course is going to be offered as a hybrid format. So we'll be live streaming this lecture to Zoom. So in case you all made it here, but there are other people, for example, who have not got their visas yet, who are at different universities. We're cooperating with the TU Hamburg-Harburg this semester. Hello online, everyone. Yeah, so if you ever can't make it, you're more than welcome to also participate online. As I said, it's a bit of an experiment, so maybe not everything goes smoothly all the time. And today the setup is a bit kind of jerry-rigged. From next week on, where we have our regular lectures on Thursdays, we'll actually have a lecture hall where there's installed equipment for hybrid lectures. So probably the quality will be a little bit better. So what is important to know is that I'll try to direct the camera and the microphone only at me. So I try not to record or film any of you. Whenever we have some longer interactions, I will actually pause the recording or later edit out the parts where we have interaction. If you just decide to speak voluntarily throughout the course, then I'll first interpret this as consent, but you have the right to withdraw that at any point, and then I'll edit out those parts where you contributed as well. That much. And if you want to ask questions and remain anonymous, there's always the option to log into the Zoom under pseudonym and ask the question there. I have an eye on the Q&A all the time. If someone happens to be in the Zoom room and I don't notice because I'm too immersed in going through the slides, then feel free, any one of you, to help me out and point out that there are questions in the chat. So a bit about me. I've been here at TU Berlin for now roughly 4 years as a postdoc at the department of Professor Tom Brown, which I guess many of you will know. And before that, I did a PhD in computer science at the KIT. Before that, I did an MSc in sustainable energy systems at the University of Edinburgh. And before that, I studied industrial engineering and economics at KIT. So you may see from that already it's kind of very mixed background. And I guess that's kind of representative of energy system modeling and energy systems, is that there are a lot of different elements that come from many different disciplines: economics, computer science, engineering, of course, which I guess most of you will be enrolled in, that all play their part in kind of making the energy transition happen, and is also reflecting quite well, I would say, what we're going to do in the course, which maybe sets it apart from the other courses you may have had with Professor Brown, where we'll actually have a bit more computer science focus. We'll be working with real data, with with one programming language in particular, with Python throughout the course. But generally, the goal and the context is all the same. In our research, we're basically using different types of tools, different programming, processing data to answer the questions how we can best reach climate neutrality or reduce our greenhouse gas emissions by mid-century in cost-effective ways. And at the group, we actually develop a set of open source software that not only helps us, but also happens to help others to do analyses in the energy system transition. So that's about me. And I also want to know a few things about you, what your background is, kind of how much experience you bring to the table, what programs you're enrolled in. So let's try to go to this Menti. And I'll actually also write down the code here so that we have it as a reference later. And I'll just swap over to that one and see how well this works. Can I see somewhere how many people are? Yes, there are quite a few people already there. I'll give you a few more seconds. Okay. So the first question is maybe a bit obvious, but kind of would be interested in what programs you're enrolled in, which are represented here. Okay, so it seems quite a few people from RIS, Renewable Energy Systems, quite a few people from PESE, and then also from other study programs, and two from TU Hamburg, and I guess a few others I also already saw in the MTS registrations. There are some kind of just different study topics that registered for the course. And I hope this is as interesting for you as it is for me. Maybe a few of the other questions, and I guess, well, for most of you, it's going to be Berlin. But maybe for those who didn't make it to Berlin to the live lecture, kind of where are you currently listening in from? Okay. Don't quite believe the Greenland or Antarctica option, but there seems to be someone from India. We can, actually not sure if it's, so someone's listening in from holiday in Sicily. Okay, good. Okay, this was more of a fun questions, I guess. I wanted to have this map inside. But you can see this, I mean, as much as this data can be trusted, maybe already the first lesson of the course, there's some people who are not in Berlin at the moment. We have for the course as a kind of soft prerequisite, so it's not enforced, it's just a recommendation to have taken kind of one of our courses from Tom Brown, Energy Systems or Energy Economics before. And I know there's also quite similar course, Sustainable Energy Supply and On and Off-Grid Systems offered in a different department that many people take while before or after taking this course. Okay, so we have about 70 people registered, and I guess should have asked how many did both, actually. Maybe you can do a quick show of hands for that, because I didn't prepare that. Who did both energy systems and energy economics already? Okay, not too many. Okay, good. So maybe one thing to say here is that there's going to be some duplication of the introductions into the different topics, because we don't assume that all of you have taken either of these courses. So there will be some foundational topics that if you have been in the energy systems, energy economics courses before, you will have heard before. I'll keep it short as a refresher and as a kind of to lift everyone up to the same foundation to be able to work with the more applied programming exercises later. Okay. About programming, so I already mentioned a couple of times that will be a part in this course. An important part, actually. You'll probably be spending most of your time doing programming while you're working for this course. So I want to ask, what is your kind of what programming languages did you already work with? It doesn't have to be kind of super advanced, just which ones you've been in touch with, let's say. Okay. So about half, maybe a little bit more, has worked with Python before. And that is the programming language that we're going to be using. If you've been using MATLAB before, structurally, it's actually relatively similar. So that will be also a slight advantage, maybe. And then also for those who have like no programming expertise, that's absolutely no problem. We'll start from the basics. We'll start really from the beginning. I'll help you with the installation, show you how that can be done. So it's really also suitable for beginners, and it's not a prerequisite to have any programming expertise. So maybe it's a difficult question to answer, but those of you, maybe 2/3 of you said they had some Python experience and maybe just kind of rate yourself or think how you would kind of categorize you here from absolute beginner to a professional. And this is also this is also for you to see kind of what your peers, what experience your peers have, and that maybe you're not alone to be an absolute beginner in programming. Okay, so my hope is that by the end of the course, I'll get you to a 6 at least, yeah? So we won't have time to make professional Python programmers out of you, but I'm sure that most of you will definitely be capable to do basic data science tasks and basic energy system modeling at the end of the course. Cool. So we'll keep the rest for later and go a little bit back to the boring admin stuff that I guess is the part of every beginning of every lecture each semester. So you made it here, so somehow you found out where the course is taking place. If you haven't found the ISIS course yet, this is the link. And this is our main communication tool as well, where I will post all the materials, where we'll handle all the assignments throughout the course. More on that later. But there are also options for you to discuss in the forum and so on and so forth that you all know from other courses as well. It's also where I just uploaded the lecture notes, and typically I would say that I will upload the slides on the day of the lecture, and as you will see, you will have seen it was very short before the lecture, so yeah, I try to do it before lunch, but sometimes it doesn't happen. But definitely before the lecture starts so that you can make notes on the PDF and so on. The other main gateway to the course is this website, this course website that you'll find under this link. It's also linked from the ISIS, where all the programming related parts of the course are. So for example, there are different introductions to different tools that we'll be using throughout the course. For example, starting with an introduction to Python, and we'll go through these notebooks together, and there will be some kind of smallish exercises at the end to get a little bit of hands-on experience before being evaluated on them. The course structure is there's basically, I would say, 4 components. There's the lectures like today, where I will introduce you to a new topic, but also perhaps with a bit more data focus and how what analysis methods there are to work with bigger data sets from various examples that I'm going to show in a couple of minutes. And that we'll typically do in the first slot of each Thursday when we meet, followed by workshops, where I'll really focus on the tools that you'll be using to work with the data. So introductions to Python libraries, kind of extensions of the basic Python. You may have heard about pandas and other tools throughout the semester. There will be some exercises, and for the assignments, there will be some consultation hours. So in this course, there will be no exam at the end, but there will be assignments throughout the semester. And before each assignment is due, there will be plenty of time to ask questions. So basically meet here, not here, in our regular lecture hall, and discuss any questions, and I'll help you as much as I can. And we have the incredible luck to be convening very late on Thursdays. So it will always be from kind of 4:15 to 7:45 in the main building. And I can also already say that in the week of the 18th of December, there will be no lectures because I'll be on holiday. Good. The courses you can take, it's basically our teaching portfolio. apart from some like things like excursion and so on. So we have energy systems, energy economics, which many of you took already. We have seminars or 2 seminars that we offer alternatingly. New developments in energy markets, which is more kind of focused on today's energy markets, and then new research in energy system modeling, which is more focused on kind of future-oriented systems, discussing recent research articles. And then there's the course you're all signed up for now. At the moment, it looks like for at least, yeah, it's a bit uncertain whether it's going to be offered in the summer semester. We're definitely offering it now in the winter semester. And I know there's been a break last summer semester, and it looks like that is going to continue just because we are a bit scarce on personnel. There's a question on the chat about the ISIS seminar. I don't think the ISIS seminar exists yet, but it will come in the next 1 or 2 weeks. So if you're interested in one of these courses, I won't go through the details. It's more for your own reference. You can browse through these options that are also offered this semester. Now, the important thing about this course is that because there's continuous evaluation throughout the semester, you have to really commit to the course at the beginning of the course. It's set up as a portfolio examination, and that means you have to register for it basically now or this week. And it's also, unfortunately, not certain that everyone will get a place. We've already upped the numbers a bit, so I'm happy to take, or I think I'm happy to take 70 participants this semester, also considering that we're not offering in the summer semesters at the moment. But to be part of the pool of potentially admitted students, you have to register via MTS. If you're an exchange student, just write me an email if it doesn't work for you. But for everyone else, it's MTS. And then we draw at random, basically, from the people who registered. There's also not going to be a waiting list. I'll slightly oversubscribe the course. So that's basically our equivalent of the waiting list. And then we only have one exception, that there's guaranteed participation for those who have previously taken the course and did not pass. So registration runs until Monday, and then on Tuesday we'll announce the students who got a slot. Of course, if the limit is not reached, which I don't think will happen, the registration period can be extended until basically the first assignment. You're always free to take it as a freie Wahl-Zusatzmodul, and as a Wahlpflichtmodul, it's part of the EVT, and I think the new EVT is SEPE. Correct me if I'm wrong. Process PESE and RACE. Okay. By the way, I mean, I know it's recorded, but if you have any questions, feel free to interrupt me either through the chat or not. I'm really happy to be interrupted. Okay, so how does the examination look like in this course? There are going to be, well, first of all, it's a 6 ECTS course as a portfolio examination. That's the kind of formal term for this kind of examination, where we have multiple elements, each contributing some percentage to a final grade. And there's going to be 3 individual assignments, counting 25% each, and then 1 final group assignment, also counting 25%. And that's the full examination. There's no final exam, but I can tell you already now that it's maybe a bit different from energy systems, energy economics, where you really need to put in more work than usual throughout the semester, but then you're free kind of at the end of the semester without having to worry about the exam. That's my tip by experience. And there's also kind of the specialty about the portfolio examination that that you can only withdraw with proven cause because you're sick for an extended period, for example, after the first assignment has been submitted. So it's a bit more difficult than in other courses to decide later on not to take the course. And we also enforce that because the capacity is limited and would be kind of unfair if you just decide 2 assignments in to not take the course anymore, because that means that someone else couldn't take this. So we have rough topics for the assignments and tentative due dates. These the last one is not Monday, it's 12th of February. These are tentative dates because it can happen that we're maybe a bit slower than I anticipate. But I can tell you already now that these are the earliest dates that these assignments will be due. And they're also listed on ICES and so on. Okay, so there's some rules for the assignments. And I'll go through the individual assignment first and then through to the group assignment. So what will happen is that roughly 3 weeks before each of the deadlines, there will be an assignment sheet that will involve some programming and some working with some real world data. And what you're required to submit, of course, it's an individual assignment. This has to be individual submissions. And it has to be answers to the questions, but including the code. So including how you got to the solution that you're presenting. You can discuss assignments with others while working on them. I actually encourage you to do that, to form small study groups or something like that, to work on the assignments. But in the end, your submissions must be your own work. So you can discuss solutions, but you cannot copy code from one another. And there's a code plagiarism detection. And yeah, basically, it is a reason to fail you if you get caught copying code. And it actually goes both ways, because also the person providing the code kind of doesn't behave in the proper way. And all the submission and the grading happens through ICES. There's a mock assignment. There's kind of an interface where you can just test how the submission works before it's actually the real deal. One thing that you definitely need for authentication is your two-factor authentication to access and submit the assignments. Good. How does the group assignment look like? Well, the group assignment, you'll get together in groups of 4 to 5 people. And what you will actually going to do, I can say that much already, you'll look at a country of your choice and plan a simplified 100% renewable electricity system with it, and present that in the final week of the semester to everyone else. So we'll have kind of this deadline, 12th of February. This is exactly the last time that we meet. And that will be not me talking, but you talking, what you accomplished in your group work. And you'll be graded based on your presentations, but also based on your code submissions, how you work together as a team. And that might sound advanced for now, but we'll do everything we can to kind of get you to that point by the beginning of the new year. And again, submission and grading is done through ICES. I do my very best to kind of, at least for the first assignment, grade it in the middle of the semester. In the past, it has not always worked out, but I'll do my best to give you kind of feedback throughout the semester. And I mean, it's obviously a bit more difficult if it's 70 of you than 40 of you, but I guess you will also agree that this trade-off is something that most of us are willing to accept. And correct me if that's not the case. What are we actually going to do? Programming and data, I said that multiple times already, but going into kind of what kind of data and what kind of tools are we going to do, to use and learn about. So we'll start with some analysis of time series. for example, of wind and solar generation and energy demands. We'll look at where can renewables actually be built, what are the kind of eligibility criteria. You maybe know that there are certain restrictions, like you can't build a wind turbine where there are natural protection areas, you have to keep certain distances to buildings, and we'll learn about tools and data sets to actually assess what areas are available. We'll think about, well, for systems with higher amounts of wind and solar generation, how can we model and determine the amount of energy storage that we need in the system, but also looking at how we can calculate power flows and transmission in transmission networks for larger systems with data sets or using data sets on the European or worldwide country transmission systems. And we'll also learn about data related to energy markets, electricity markets, how they work, and how we can maybe try to model a system that it reproduces historical price outcomes, for example, so that we can always, I mean, the modeling side is always about trying to learn how the system behaves, not necessarily about predicting what is going to happen. And so kind of a good check for any model is whether it actually reproduces what has been observed in the past. That's some of the things that we're going to look at. And then the last 3 bits are a bit more, the system planning sector coupling are a bit more future oriented about aspects that come in from now on and how the system evolves into the future, where there's electrification, there's more electric vehicles coming in, there's heat pumps coming in, and also the industry sees big transitions. And how do you actually plan a system, or how do you model, or how do you create a model that can help you with planning the system and knowing what the big trade-offs are, where should you build your wind turbines, your solar panels, what storage should you combine it with, and do you actually need electricity transmission or maybe a hydrogen network, and this sort of things we're going to look at. One kind of gimmick at the end is that we're actually also going to look at interactive visualization tools. So one thing that is always a struggle with bigger energy system models is that how do you interpret this data? It can be like big amounts of tables, big amount of data, but then as almost an art to produce kind of insights from it, and interactive visualizations help, especially if your data sets are a bit bigger. So this is your reference for the rough course schedule. You might adjust that semester a bit, but you'll see here that there are plenty of elements for the consultation hours for the assignments, and especially for the group assignment, there's kind of more room where I can help the groups make decisions on what they want to look at. So what should you take away from my perspective by the end of the course? This is my goal for the course, to teach you these things. And these, I mean, these basically mirror what we're going to talk about in the course. So I want you to really work with data and an evaluation of the renewable potentials from geographical perspectives, from temporal perspectives, but also maybe socioeconomic perspectives. I want you to have used the models so that you can build an understanding of what the challenges are with integrating the renewables, what concepts there are to what concepts as solutions there are to integrate the renewables, and how you can use the models for that, and how you can also interpret the solutions. So I'm going to say from the very beginning, these models that you'll be working with, they are simplified. They will always have flaws, and even the most sophisticated models that you see in research, in industry, they all have flaws. And it's important to know kind of the limitations of the models and what you can interpret and what you cannot interpret, and what you cannot conclude from them. So that's also one goal I have for this course. And then generally, I want to up your programming skills. using open source tools, so not relying on any commercial tools, and also learn about the kind of magnitude of data sets, public data sets that are around to help you assess in the various dimensions of the energy transition limitations, potentials, and system interactions. So that's kind of my rough idea for the course. But maybe also kind of let's mirror this question to you. I mean, you all had probably some thoughts about coming here, what you want to learn, and I would be curious to see whether that roughly aligns with my plans. And if that doesn't, then I'm happy to kind of take small detours. So if you have something that you really want to learn about, then I'm happy to take this as a kind of as a nudge to include that in one way or another in the lectures. Yeah, and it's going to, whatever you write is going to come up here. Okay, so what I read so far is all quite similar. It seems to be about improving your Python skills and especially using a tool called Pipesa, which is one of the tools that we develop here at TU Berlin. It's kind of one of these open source tools that let you model energy systems from kind of small scales to bigger scales, from simple models to complicated models. So yeah, connection between Python, using Python tools like Pipesa to model energy systems. And maybe apply that to particular countries of interest, maybe to your home country, your home region, and prepare for your master's thesis, also one aspect. Okay. Yeah, so that sounds pretty cool and practical to do, and aligns with my idea about the course. So I'm happy with that. So let's see if I forgot something. Yeah, so visualization and data analysis also mentioned. So actually, the Python Pipesa modeling will be kind of starting halfway throughout the semester. So we'll really spend the first steps in the programming to learn about the basics and learn and work with pandas, for example, and some geographical GIS data or GIS tool extensions like GeoPandas, for example, to work with the underlying data that we then eventually put into energy system models like Pipesa. So yes, that's that. And yeah, I actually brought some additional slides to give you, like, this was the boring admin part, and brought you some kind of invitation, some context setting, some motivation for why this is all relevant. And I kind of try to categorize that a little bit in a way that it actually shows some of the data sets that in part we're going to be using, but in part I just think are quite cool that they exist and that they highlight kind of some of this data availability, tool availability to showcase or they show that this data that we need to analyze how future energy systems with zero or net zero carbon emissions might work actually exists, is lying around, and there are actually some pretty cool tools around it. So most energy system model course started with something like that, and probably we don't need to talk about that in detail, but here's a short recap. So we have on the one hand side, we have kind of really high rise in worldwide, mostly fossil energy consumption. But on the upside, we also have, for the past decade or so, we have wind and solar really catching up. Wind and solar, especially for the solar, but also for things like batteries, we've actually also seen quite drastic cost declines. So that also helps kind of bringing the renewables further into the system. And that's absolutely necessary because to avoid the catastrophic consequences of climate change, really need to be phasing out these fossil fuels and bringing in more renewable resources or low carbon resources. Doesn't necessarily have to be wind and solar, but just happens to be a resource that has kind of declining costs and is broadly available across the globe. And we actually need to do this quite quickly, ideally by mid-century, to get to net zero. That's very fast. That's a big industry, big transition of the global economy. And of course, not all the systems align. The difference come from different models that make different assumptions about all the different fields. There can be model errors because things are simplified. There are a lot of things are uncertain. We don't know for sure what certain parameters are going to be. We don't know for sure what certain costs are. So there's kind of always a bit of disagreement between models, not only in models that predict or that show pathways that would be meeting the kind of 1.5 degree or 2 degree targets, kind of models that are more about kind of climate systems and so on, but also you'll see similar things in energy system models. No two models will spit out exactly the same results for whatever reason. So to reach these targets, actually countries across the world have made all these different pledges and targets to kind of limit the global warming. It's not nearly enough what the kind of actions and policies implemented are to reach the targets these countries committed to, but nevertheless, they're ambitious and have triggered kind of developments already in today's system that kind of lead to more renewables. We have seen support for solar, for example, subsidies for solar, and kind of technological development in kind of various different technologies that will play an important role in future energy systems. But the big question that kind of our research here at the chair is concerned with is, how do we actually reach these targets? So we mostly look at normative scenarios where we say, okay, we take it as a given that society or governments, society have decided that we want to reach these goals. And the question then is, how can we really implement that? How can we implement that from a technical perspective, taking into account the challenges of the variability of the renewables, but also from an economic perspective, how can we do it in the most cost-effective manner? And then there's also a social dimension to it that we perhaps are not very strong at in kind of analyzing, but there are other researchers around to look at the social dimension, because we also want to reach this in a way, or you might say we can only reach this if there's also social or public support for the solutions that are proposed. And perhaps there are some trade-offs between going for something that is maybe slightly more expensive, but socially more accepted. So this is where energy system modeling comes in to really look at what trade-offs are there, and looking from under technical constraints, we need to, well, whatever we model, we need to be roughly technically feasible, because otherwise, what does it tell us? But then we can play out different scenarios, different cases, different assumptions that we make about how future things might develop, different kind of social trade-offs. Do we want more wind, more solar? Do we want more transmission lines and transmission towers, or focus more on the storage? And energy system models are really just a tool to analyze what trade-offs there are and how things could develop under certain assumptions. It's never really about predictions. It's always about comparing different scenarios against one another. Also because these models are, there are uncertainties, and these models are not exact. And things or questions you might ask people or use energy system models for to answer from kind of today's perspective or tomorrow's perspective is, maybe today you're worrying more about how we can restart a system after a blackout. Does that work? We have seen the energy crisis a couple of years ago with high gas prices, and studies could maybe and maybe 5 years ago or 6 years ago, people should have done some studies about what a price shock in the gas prices would actually do to the system, because that would give maybe some guidance to policymakers about how they can be mitigated, how risks can be hedged, and so on. And also generally how kind of policy changes would impact the system. So for example, just to pick out one example, when Germany phased out its nuclear power plants, there was a lot of debate about how does it affect the electricity prices. And of course, we can say now, looking back at the prices, we can look at the historical data, how it actually happened. But for the discussion, we could have used energy system models, and probably there were people who were doing this to kind of study one case where the nuclear continues to operate, one case where it is kind of phased out, and then look from the model what the prices are. And you can do all sorts of similar things about future energy systems, how this transition can happen, what infrastructure it needs, how the system would operate in this case, given the variability of the renewables. And then perhaps you also have this kind of these aspects of policy changes in there where you maybe want to try a new market design and see how it behaves in such a system. You can perhaps already imagine that this will kind of answering all these questions, whether it's from today's or tomorrow's perspective, is quite complex. It involves many interacting parts. We can't calculate it on a piece of paper. We have to put it into models, and these models, they don't work by themselves, but we actually need to process a lot of data about existing infrastructure, existing market rules, existing policy rules, to have these models actually represent something that mirrors reality. And kind of this is the point where our course comes in, where it's really about learning to apply the tools and methods from data science to digest this data, put them in the models, and then be able to apply them for several study cases. For example, how a country could become how a country's electricity system could become fully carbon neutral. So I'll run through a few data sets, but before I do that, I want to maybe spend a few minutes to collect what you think, what data sets we'll be working with. So what kind of data? So I'll give one already as an example. We probably need to look at wind and solar time series, how the variability is. And can you come up with more examples? Okay, let's start to digest it because before the font becomes too small. I already saw a few things that are right. So weather data, yes, that's quite important. It's the obvious things like wind speed, solar irradiation, but there's also temperature that plays a role. I'm not sure if that's here somewhere, because if the temperature is low, the heat demand is high, and when we want to electrify that with heat pumps, then that's relevant. Grid data, yes, I'm going to show you an example later about when we need to plan how maybe the transmission system operators plan to build new transmission lines to connect offshore wind, for example. We need to assess that properly. We need to have a good idea of what the current capacities in the grid are. Market prices is another good point, but it's it's considered in a very different way often, is that market prices are often a result of the optimization of the modeling, but data on market prices can also be a very useful validation tool where you can check whether the prices that you receive from your model, if they match what has been observed historically under similar conditions, then you can be then that's a good indicator that your model is not completely off track. Yeah, so I think there's probably something on power plants as well. I saw something earlier about Wasserkraft, yes. Somebody see something? Cable lengths, that's right. Okay. So not only Wasserkraft, which is hydropower, but also capacity of all the power plants that are existing, may it be gas, coal, or renewables. Where do we actually have already wind turbines and solar panels? These are kind of, here it is, power plant capacities. Great. Population density can be quite useful. If we have, for example, country level statistics about energy consumption, we maybe want to distribute that to a coastal region, and we then actually need to combine two different data sets to get the resolution that we need. It's, of course, then always an approximation because it's maybe not a one-on-one mapping that the energy demand distributes by per capita, but it's maybe sometimes a good enough approximation. Right, so consumption data, that's important. Kind of what are we producing the electricity for? There's also demand time series, so there's this temporal component for it as well. And generally, I saw some aspects on kind of policies. What policies do we actually want to put into this model? So all good points. And some of these points you'll see in the upcoming slides. And we're not going to open up all of these examples, but some of them we might do a more detailed dive into. Who has seen, quick show of hands, who has seen this website before? Okay, so it's a global wind atlas. So it's a kind of resource. I think it's primarily developed by the DTU, Danish Technical University near Copenhagen, where you can actually see what the kind of average wind speeds are in the different regions. For example, kind of North Sea area, UK, Ireland, it's quite windy, so probably it's quite good to place the wind turbines rather there than, say, somewhere in northern Italy, for example. Just picking out two examples, and this global data set, so you can actually also look at other regions like Morocco, Namibia, Argentina, Australia, and so on. And of course, if there's a global wind atlas, there's also a global solar atlas, where you can look at the solar irradiation. It doesn't surprise you probably as well that the further you go to the equator, the bigger your solar irradiation is. But I should say that this is not all, because in these data sets, you don't get the time series. So for example, there are some regions in the tropics. Maybe from a European perspective, we always assume like, oh, lots of wind, lots of solar in the summer. But then if you move to some regions closer to the equator, then you have a rainy season, and then you actually have the reverse pattern that is actually less sunny throughout the rainy season in the summer. So you have actually different temporal patterns depending on where you are. And then, of course, if you go to the southern hemisphere, everything is inverted as well. But it's never quite a one-on-one mapping. And things you can see here, maybe from a European context, maybe it makes more sense to build solar turbines in solar panels in Spain rather than in Scotland. And kind of obvious, but then it's always also a question of, well, the demand is maybe here. So putting the renewables or the capacities of wind and solar in the regions where the resource is the best is maybe not always the best idea. Maybe it makes sense to actually, and I'm making some examples up, maybe it's better to build the solar panels somewhere here, so that's actually close to the German industrial clusters where there's a lot of electricity consumption, and we don't need to build that much interconnection from electricity grids or hydrogen even to get there. And this is, in many cases, is a non-obvious trade-off. And that's why we just kind of collect this data, collect the facts, and then put it into a model so that the model can evaluate under kind of known methods, known theory, what is the cost optimal way. And then we maybe want to nudge the model into kind of not cost optimal ways, but maybe more socially accepted ways. And while you don't get the time series from these two data sets, You may have heard about Renewables Ninja. Who has heard about Renewables Ninja? Okay. You can actually go there and collect the um, time series. So maybe someone who's logged into Zoom can post in the chat what country we want to retrieve some time series data for. And the first person who writes the country wins. See how long this takes. Okay, Peru. Okay, so that's now challenging my geography skills. But yeah, we can go to Peru. Let's go maybe more to the south, and we can go here, collect this point, and then make a few selections about, I think the year is just set to be 2019, a historical year, but we can, for example, check whether we want to have some axis tracking where the solar panel moves with the solar inclination. Maybe in this case, we want to keep it fixed, and whether it's south oriented or not. So 180 degrees would be south oriented. We can run this, it's very quick, and then we get actually kind of the solar production profile as a daily mean. You can see here kind of some seasonal trend of the solar availability. We're still in the northern hemisphere. So are we? No, we're not in the northern hemisphere. The southern hemisphere. But then it's a bit okay, interesting. But anyway, we have some seasonal variation of the solar, as you will see in many regions of the world, even around the equator, because of rainy season. And you get the same for wind turbines. You can even do that since recently for heating and cooling demand, where maybe let's go to the UK and look at the heat demand there. Oh, let's see. So yes, here you can see a typical profile. So almost no heating demand throughout the summer, and then kind of has this classical seasonal profile of high heating demands in the winter. And this is kind of another challenge that we see in energy systems, future energy systems. You have technologies, supply technologies that have maybe a completely opposite seasonal profile than the demand. And that makes it necessary to think not only about kind of where to place the different resources geographically, but also how we can maybe transfer some energy from one point in time to another through storage, different types of storage, basically. It can be battery storage, probably not, because it's maybe expensive to store it over a long time. We'll get to that at some point in the course, or through some form of chemical storage, like hydrogen or yeah, some other derivative that you make from hydrogen. Yeah, so kind of, and here you have, I mean, a system in the UK that you would build 100% in solar that also uses electricity for the heating demand, probably quite challenging to align. Not saying it's not possible, but definitely something to consider that you have completely opposite periods where the demand is versus when the supply is available. Okay. So about um, so we talked about the resource now, both on the geographical scale, but also on the temporal scale. But the resource is not everything. We also maybe have restrictions of where we can build a wind turbine, for example, or PV panels. I mentioned at the beginning distances to buildings or natural protection areas, but also things like very mountainous areas or forests. They play a role in where you can place the wind turbines. And Agora Energiewende, kind of think tank NGO based here in Berlin and Brussels, came up with this a nice tool, which I'm going to show you. that lets you actually explore interactively where there's actually where there is oh, that's not what I wanted. What happened? Nothing. Okay, nothing is good. Where you can actually zoom in. Let's say we zoom into Berlin. Well, it's not really, the default here is quite strict. We have, sorry that it's in German, but we have 1,000-meter distance to settlements, buildings. We don't allow any use of forests, and we don't allow any use of natural, it's kind of a lower tier protection area than natural protection areas. It's kind of one tier below that. And let's see whether we can actually make it happen that there are some potentials in Berlin. Yes.
Already existing?
Probably not. No, probably not. So that's, yeah, and I think there are actually wind turbines in Berlin. And some of these models, they're not perfect. They idealize a bit. And this is, of course, it's a kind of data set for all of Germany. For validation, they probably didn't look at Berlin as they didn't fact check. And there's actually a nice paper. Sorry, I take a detour now. It's by this researcher from Sweden, who made exactly this comparison about kind of looking at analyses like this, where you take into account a bunch of different data sets, look what the exclusion areas should be according to the rules, and then look at where actually the wind turbines were built. And the funny result was kind of that there are actually quite a lot of areas where wind turbines were put, although with these analyses you wouldn't see it. I'll find it and post it later in the ISIS. It's not sharing. Okay. Okay. That happened. Okay, good. Now that's clear. I think you can see it now again. Good, excellent. So let's go back. So actually, kind of when we relax this distance to the settlement areas, we actually get a bit. So I didn't prepare this. So is that Tempelhofer Feld? Oh yes, it is. So maybe at some point we'll see a wind turbine there, and maybe it's not a good idea. Okay, not trying to get too political about this. This is kind of one other important factor. Not only the resource is important, but also the social constraints about where we can build things. And we're actually you're going to do this yourself in a couple of weeks' time. Not for Germany, but for some other country, and do these analyses. So example topics that are relevant here, kind of what are characteristic time and regional patterns of the resource, what land areas might be available, and then there's also an economic component to it. What could be the cost difference between building a wind turbine in Berlin versus Brandenburg versus Bavaria versus Patagonia? Yeah, kind of this much about the renewable potentials. So many of you also mentioned existing infrastructure, and I brought two examples here. Kind of data on where are actually capacities and locations of existing power plants and of what type. There's this very nice website, Global Energy Monitor. Has lots of data sets on kind of energy-related topics, like where coal mines are and things like that, where LNG terminals are and so on, but also this integrated power tracker. And again, while I sum that up, maybe someone in the chat can write a region we could look at more closely while I introduce the data set to you. So this is really a global data set. So these people, they've been funded by philanthropists that kind of collects really data about all the different energy carriers. Maybe let's remove the wind and solar because that slows things down. And Rwanda, So wait, this is somewhere here. Yes. Okay. So we can zoom into Rwanda, and there's a Lake Kivu power plant, 56 megawatts. So that's a relatively small power plant. There's a 72 megawatt, also fossil gas, a smallish power plant. And then there's also a hydroelectric plant here, 44 megawatts. So kind of small energy system. As a contrast, we can maybe go to France, where you have traditionally a lot of nuclear power plants. And then if you go to just one of them, what the rate here is, it's actually 3,100 megawatts. You can see not only what the capacities are, what the type, what the fuel is, but also what the status are, whether it's still operating, whether it's what the number of units are, and when it was built. And when it was built is also quite a kind of important information, because that determines that determines when it's going to be phased out, when it reaches its lifetime. We have a similar data set. So on the global power grid data, this actually comes from OpenStreetMap. So you may have used OpenStreetMap for navigation, and you can actually also extract some information on the grid data. So here I'm going to zoom into Berlin again and show you. So this kind of shows you different high voltage power lines in Germany, and the colors just indicates the voltage level. So the purple here is the highest voltage level that is there for Germany. And I wanted to show you that actually we're very close to Berlin's 400 kV transmission line. So we are currently in this building here, and just across the street, so I think over there is where the voltage line is. It's underground here, so it's also kind of special for Germany that most transmission lines are overground, and this is actually one of the few that is underground in Germany at the moment. Fun fact. And nice thing is that you can really see go to areas like Ireland, to Galway, for example. And you can see not only the high voltage level, but you can even see how the different households are connected. Not everywhere the coverage is so good, but this is actually data that kind of is community-based. People have collected this data and made publicly available. And that, of course, makes it much easier to do kind of research with this data available. So existing infrastructure, what is interesting for us, what kinds of power plants dominate the mix in different countries, what's the age structure, but also could be other things like in the energy crisis, we talked a lot about LNG import terminals, for example. This data you can also find. And then for the transmission lines, it's of course important to know kind of where are going to be the bottlenecks in the transmission network and how can we calculate the power flows there. Okay, last segment before I let you do something again, electricity markets. So this is maybe not so much about input data, but more about kind of historical observations about things we know, how the market works, what the market outcomes were. And there's this website here that people from Fraunhofer Institute put together that kind of shows you for an exemplary week, you can actually go to this website. There's a lot more here, but we're just going to focus on the electricity production. You can actually see compare the black line, which is the consumption at the moment, to the electricity mix, how it is being produced. So at the moment, I think, let's go through the colors. The yellow is obviously solar, the greenish colors that are wind, and then what is it? Orange is gas, black is coal and brown is brown coal, and then we have some biomass and hydro also in the mix. So actually, we have very little renewable contribution at the moment. We can go back. Let's go back a random week, somewhere maybe a couple of weeks ago, 12 weeks. Yeah, something like that, where you actually have also periods where the wind and solar were much stronger in the mix. And it can sometimes always be quite interesting how the system operates. And it's also useful data, as I said before, to validate if we have a model, does it actually reproduce roughly this electricity mix with the data that we feed it. And kind of analysis of this, how the electricity mix works, is also used in other ways. For example, in this data set from electricity maps, it doesn't show you anything about the electricity, but it shows you how dirty or clean the electricity mixes that you consume, and that can be relevant for big electricity consumers like data centers, for example, that want to know kind of or attribute in some way how clean is the electricity that they produce. And I think we have time to oh, that changed from before. Let's hope they didn't put it behind. Oh no. Yes, I'm ready to get started. Yes, okay. Good. So what you see here, you have, for example, Norway with particularly green mix. Germany doesn't look too good at the moment because we saw earlier quite a big amount of fossil fuels. And then you can actually see that by the different market areas. So for example, Italy has different market areas where electricity is traded, and so do countries like Sweden and Norway. And yeah, you can go, for example, here. You can see in Australia quite nicely, South Australia, like around Adelaide, actually has quite big penetration of solar, as more frequently green than the surrounding states, which are also still quite coal-based. What you see here measured is kind of the grams or the average grams of CO2 emitted per unit of electricity that is being consumed. So it's just a kind of metric of how clean your electricity system is. It's of course quite contested how that is being used. What you will also find is you find the market clearing, and that's one other frequent aspect that people put in the word cloud before. That kind of we also want to know for the electricity mix, what is the price of the electricity that we pay? So here's an example where there were relatively low prices. That's from probably a year ago, where there were very low prices all across Europe, 14 euros per megawatt hour. But you can also find cases where there's a lot of price divergence between the different market zones. And that's typically an indicator of congestion, that kind of cheap electricity that you find in maybe one region cannot be transported to the region where it would be expensive. That would, from an economic perspective, of course, make sense. But then it's maybe not possible because of the grid. So I would say, first of all, things that we're going to look at here is how do electricity markets work? Can we actually reproduce that from models? And then we are not only interested in reproducing outcomes, but also deviating from them on purpose and see what would happen if the CO2 price increased, what would happen if the gas price increased, what if we phased out the coal and the nuclear power plants, what happens if the nuclear power plants in France are not available, or the hydroelectricity cannot operate due to droughts, and make some kind of assessment of how critical these periods can become. So I think I already saw that most of you have somewhat a laptop or some, if not a mobile phone working. So I would say I've been talking already quite a long time, and I'll give you the chance to get together with your neighbors and maybe get to know some new person, to do some exploration tasks yourself based on the data sets that we just looked at. And maybe try to do that in 10 minutes or so. And I would say kind of you can pick A, B, or C. Don't do all of them at once. Pick based on your interest. There's one exploring more existing infrastructure. For example, finding the transmission line that is closest to your current home or closest to your last holiday location, as well as a power plant. You can look at more at this energycharts.info, finding a week where there was maybe very high renewable feed-in, or look more in the wind and solar resource and finding kind of pairs where there's both high wind and solar resource or both low wind and solar resource. So I'll give you free choice and 10 minutes to just work a little bit and explore yourself, because I know it can be quite tiring to look at all the different data sets. Okay, so I hope you had some nice insights. I mean, we won't discuss it as a group, but I just hope that you found something that is interesting and maybe got to talk to some new people. For the remaining, so I'm wrapping up now, basically. There's a few more things that you can explore, and feel free to go as a kind of follow-up to this introductory lecture through some of these data sets that we talked about in your own time. There are also some that are more related to planning that we didn't get to today, but that's not really a big problem. You've seen enough different data sets today, just flashing here that there are some data sets that you know about what transmission system operators plan, what pipelines, and in this case, transmission lines are planned. There are various platforms that kind of try to track where we are at in today's energy system. So you may have seen this on Site Online. Who has seen this on Site Online before? Okay. Anyways, kind of especially during gas crisis, and you saw these kind of dashboards also throughout Corona, non-energy related topics about looking at what the gas storage capacity filling level is, for example, where just the general public is also more and more exposed to this kind of data, where the wind capacities are built, where the solar capacities are built, and whether we are actually on track of meeting our targets. So this is another example here by colleagues at DIW here in Berlin that really look at what are the government targets of the different for the different energy sectors or different aspects, going from renewable electricity to provision to smart meter rollout, through electricity prices, e-mobility, how many EVs are built, and to see whether they actually align with what models spit out as what we need to do to get to climate neutrality in time and what has been politically decided. That website is really quite insightful if you want to see whether we are on track. And this tool we're going to use later, not today. That is kind of a small example of what these energy system models actually spit out, but we're going to do that next time. So really, kind of once you have all these different data sets together, you're thinking about more future-oriented systems. You're looking at questions like, what is the optimal ratio between wind and solar? How do you manage the variability? And you really want to quantify that, see how much of a certain type of storage technology is built. For example, how much grid expansion do we need under certain conditions? And then there's, of course, the looming challenge that we actually not only want to make our current electricity consumption renewable, but also our general energy consumption from buildings, heating, transport, and industry. So that will come at a later point in the course. We develop here in the group we develop different tools. So pipes are here is something that we develop here that you all asked about. But this all builds on several other kind of data sets, several other tools that we need to introduce first. And that's what we're going to spend the next weeks on getting you up to speed there. And example functionalities include all the things that we talked about in this lecture: time series, processing geographical data, working with networks, building these optimization models, and then eventually visualizing the data. So if you're interested in more what tools we develop as a group, there are 3 slides of things we do as a group. You can go through that in your own time. What I will leave you with for next time is what you can do to prepare is the kind of go to this course website, go through the introduction, and maybe try already to install a Python version on your own machines. It's not 100% necessary, and next time is also meant to kind of help you with that, but it doesn't hurt if you tried before. And I'll leave it at that. I'll see you next time on Thursday next week in a different lecture hall.